Welcome to strong form induction. So this is going to be very similar to weak form induction. The whole structure is the same. We prove it for a base case, we make an induction hypothesis, and we try to say, can we prove it for the next one? The only difference is the induction hypothesis, right? So in weak form, what was our induction hypothesis? We assumed it for some k, and then we tried to show it for k plus 1. So all we did assume was that predicate for some k. But in strong form, we're going to not just assume for k, we're going to assume that's true for k and for k minus 1 and for k minus 2 all the way down to our base case. All right. So in other words, weak is just assuming the step before. Strong is assuming all the steps before. Okay. So you might say, well, why does that matter? And we'll talk about it with a little example. We're going to prove the fundamental theorem of arithmetic, which sounds daunting, sounds scary, but strong form induction is so powerful. This proof is not going to be that bad at all. Okay. This will probably be a lot better than some of the other proofs you've done for this induction stuff. Okay. So this says that any integer bigger than 1, so, any integer bigger than 1 means at least 2, can be written as the product of one or more primes. So, right, for example, if we look at the number 6, right, that's 3 times 2. If we look at the number 12, that's 4 times 3, but 4 is not a prime. So it's 2 times 2 times 3, right? Everything has a unique prime factorization. If you remember going, whenever this was, right, and having to fully factor everything into just prime numbers, that's what this is saying. It says any number can be factored into primes. So how can we prove that? Well, the exact same way we've been doing other induction, we're just going to assume a little bit more. So we'll start with our base case. All right, what's the smallest case this is true for? Whatever number is bigger than 1, it's 2. So for n equals 2, well, yeah, that works, right? 2 can be written as itself, right? That is a product of 1 prime. Remember, we say product of 1 or more primes. So, yep, there we go. This is kind of silly. Kind of feels a little dumb to write this out, but that's all we need. We just need to show that, yeah, it does work for that first case. And 3 would look the same. 4 would be a little bit more interesting. We would show that 4 can be written as 2 times 2. But we don't need to do any of that. Let's look at the induction step. And this one's going to look a little different because now it's strong induction. So we're not just going to show that P of k implies P of k plus 1. We're going to show that for all I that are less than or equal to k, that P of I is true. This is our induction hypothesis now. Okay. Notice that good predicate logic with that universal quantifier. This is our induction hypothesis. And we're going to show that our induction hypothesis will show that it's also true for k plus 1. This looks messy, but again, remember your logic. Remember your predicate logic. All this is saying is this. We're assuming it for k minus 1, for k minus 2, etc. That's all that's saying. So how can we do that? Well, hold on. My cat is sitting on my notes. Sorry, I woke her up. She was not very happy about that. Okay, so and this is where we also introduce something that we're going to talk about 2 videos from now, something called proof by cases. Because when we do prove, right, we want, right, what do we want? We want to show that k plus 1 can be written as a product of primes. Okay? And it's a little annoying to write, but it's so useful. That's what we want to show. And what do we know? We know what we're assuming, right? This induction hypothesis that 2, 3, 4, etc., all the way up to k, can be written as a product of primes. I'm not going to finish writing that. So we know that every number less than k plus 1 can be written as a product of primes. So can k plus 1 be written as a product of primes? And it kind of depends on whether k plus 1, is this new number a prime number or is it not a prime number? This is proof by cases. We need to know whether k plus 1 is prime or not. So we're going to break this down into steps. Okay, so let's say, case 1, if k plus 1 is prime, what happens? And then over here, we'll also look at what happens if k plus 1 is composite, if it's not prime. So we can't continue the proof unless we know whether it's prime or not, because it's going to be a different situation. So we're just going to say, well, what happens if it's prime? What happens if it's not prime? And if those are the same thing, then we can say it'll happen regardless. Again, we'll talk more about that in 9.3.6. Well, if k plus 1 is prime, this is very easy to show. If k plus 1 is prime, then yeah, it can be written as a product of primes. It can just be written as itself like we just did with 2. So this is easy. So if this is the case, well, then we're pretty much done, right? K plus 1 is just k plus 1, which is prime. We did it. Now, if k plus 1 is composite, then what does that mean? That means there exist 2 integers, using some nice shorthand that we learned, right? There are 2 integers that are both strictly smaller than k plus 1, right? It's going to have factors, and the factors have to be smaller than the thing they, multiply into, right? This means n times m is equal to k plus 1. So, they have to be smaller than k plus 1. These are our factors, right? We have 2 factors that are smaller than k plus 1. Ooh. So k plus 1 is n times m. We know this. And we know n and m are going to be natural numbers. Honestly, yeah, here, let's not say integers. Let's say natural numbers. And k plus 1 will be equal to that, right? That's the definition of composite. Composite means it can be written as 2 natural numbers times itself. Well, really, we're saying natural numbers of 2 or more. Okay? But since these are less than k plus 1, our induction hypothesis says each of these, right? Induction hypothesis says each of these can be written as a product of primes. Oh, what does that mean? Well, if each of these can be written as a product of primes, well, we have a product of primes. So this is a product of primes. So if k plus 1 is composite, it has 2 factors. Those factors are smaller. Our induction hypothesis says that, yeah, any number that's smaller, right? We said that was true for anything less than k plus 1. So it's certainly going to be true for these 2 factors. And if those can be written as a product of primes, then this is a product of 2 products of primes, and it is itself a product of primes. And we're good to go. So no matter whether we're prime or composite for that next k plus 1, we've got it covered. So we showed base case. We showed the induction step. So by induction, this is true for all n at least 2. And we are done. That's how you prove with strong induction. So very powerful. All right, sometimes it's a little, well, actually, I'll talk more about the difference between strong and weak induction later. But again, the idea here is that you use strong induction when you need more than just the previous step, right? We're not factoring into the number before k plus 1. we're factoring into any, who knows what numbers, all the numbers, sum of any of the numbers before k plus 1, right? So in that induction step, we do have to use both of them. That's kind of when you're going to use strong induction. Let me know if you have any questions, and we'll do another example in the next video.